of how we make alcohols. And then anything left over with alkynes. Did I go through the mechanism for making for the keto, for the tautomerism? Did I write a complete mechanism for that last time? I'm trying to remember. I don't know that I did in this class because I kind of ran out of time. So let me just go back and mop up some things. But again, if you have a question, ask. Otherwise, we have two choices. We can either start doing the problems on the worksheet, or I can go back and mop some of this up, which I'm going to do that. So here is a terminal alkyne. And if I was to ask you to write the full mechanism for hydrating an alkyne, what would we write? And I'm going to write this reaction without transition states, which we tend to do a lot more of this semester, writing without transition states. But what would be the intermediates of this reaction? So we already know what the first step would be. I'm going to react a triple bond with H+. So I'm going to take that pair of electrons, move it towards the H+. How am I going to add the H+? I'm going to add it by Markovnikov addition. So in this case, there's a terminal. It's a terminal alkyne at the end, so I'm going to add it to the right carbon, to the carbon with the hydrogen on it. And so I'm going to end up forming a carbocation and add the hydrogen then to the end carbon. So this is a carbocation, just like I would have written if I would have taken a double bond. The double bond would become a single bond. In this case, the double bond is going to, or triple bond is going to become a double bond. Next step. H2O is going to come in and add the whole water molecule, just like we did last semester. Right? We do not break up water. The whole thing adds. So we end up with the oxonium ion. And then final step is going to be lose the H+. So the H+ was a catalyst. It still is. Now what's different about this reaction than the one we did last semester was that now now I've got a double bond and the OH is attached to a carbon, bless you, with a double bond. So this is what we call an enol. It's half alkene, half alcohol. For the most part, enols are not stable. These run-of-the-mill ones that are pretty simple are not stable. Why aren't they stable? The reason they're not stable is because it would be far more stable to have a carbon-oxygen double bond in the molecule. So this is going to want to rearrange to form the carbonyl. And we're going to see that next week. In general, if we can form or reform a carbonyl, we will, because it's a very stable bond. So in this case, what happens is this pair of electrons moves to form the CO double bond. At the same time, this pair of electrons moves so that I can now bond that hydrogen that I just put in the square. So then I'm going to form the CH bond. You could probably move the electrons in with opposite arrows, but this is the way they really should go. And so what I'm going to end up doing then is I'm going to end up forming I'm going to go ahead and write both these hydrogens out explicitly. I'm going to end up forming the ketone, and then the hydrogen that's in the box moved from being attached to the O to being attached to the C. And it turns out that this, which is now a ketone, that ketone is more stable than the enol. So if I asked you to write this on an exam, which if you look at all the old exams, it's usually something I ask you to do, this would be the complete mechanism of hydrating an alkyne. So it's not just enough to form the enol. You've got to take it all the way to the ketone.
So is the arrow, let's say, breaking the double bond, is that going?
Yes. It's being used to form that CH bond. So that would be the mechanism for not only the tautomerism, but also then for the entire mechanism. And tautomerism means that not only am I moving pairs of electrons, but I am actually moving a hydrogen. So if you look in your book, the definition of tautomerism will be the simultaneous movement of electron pairs and a hydrogen atom. These are not resonance structures, because in resonance structures, the one thing we are never allowed to do is to break or make bonds. That's not allowed. And in this case, I did both. So this is a tautomerism. So it's actually the arrows would be for this, the arrows are a set of equilibrium arrows. And sometimes people get that confused. They'll call these resonance structures when they're not. I think when Dr. Weiner and I submitted a paper on this, one of the referees came back and said the resonance structures, and we're like, how sad. They're not. They're tautomers. It's equilibrium. If they were resonance structures, neither one of them would exist, right? It would be the hybrid. These are true structures, and they both physically exist. If you take PChem lab, you'll do an experiment on determining the percentages of each one of these two in a mixture. So that's the mechanism for hydrating. Does that make sense? The only new step here is the tautomerism. That's the new step. Hopefully everything else is kind of like, oh yeah, we did that a lot last semester. Except in this case, we're not going to put in transition states. Now what happens, this is truly Markovnikov, because this carbon has 0 hydrogens, that carbon has 1 hydrogen. So what would happen if I take a problem like what was on the worksheet from Wednesday? What if I had an internal alkyne that was not symmetrical? So if this thing is symmetrical, if this is a symmetrical alkyne, then it doesn't matter where you add the H and the OH, because when it tautomerizes, you're going to end up with the same product. But if it's asymmetric, meaning there's a methyl group on one side and an ethyl group on the other, what's going to happen? And what's going to happen is that there is no Markovnikov addition, so I need to add the H and the OH to each carbon. So I'm going to have two combinations here. So if I said, what's the product or products of this reaction? We'd say H plus H2O, what am I adding? H and OH. And the triple bond is becoming a double bond. So if I'm writing those two products, I would end up with adding the OH to the middle carbon. I would end up with that. Adding the, well, they're both middle carbons. So I'd add the H and the OH left and right, and then vice versa. So these would be my two enol products. And they would be formed 50-50. And then once these enols convert themselves to the ketones, the OH group becomes a carbonyl. The H ends up over on the other carbon. So for the left molecule, I end up converting that enol into that ketone. For the right-hand molecule, I'm going to do the same thing. The H is going to be moving to the carbon on the left, and then the right carbon is going to become a carbonyl. So now I have my two different ketones, and they are different because one would be 2-butanone and the other one would be 1-butanone. The carbonyls on carbon 2 versus carbon 3. And I would make these products 50% of each one, so each one, these two would be the major product of the reaction. So if it's an internal alkyne, there is no Markovnikov. Sarah? For the enols, yes. So for the enols, if I was really being careful, I would say that I get both of those products where the H and the OH are cis and trans, and over here I would also get cis and trans. Because it goes through a carbocation intermediate, so it would be, so you would add H and OH 50-50. In this case, though, you could say, do I have to do that? The thing is, for this, for the final products, those two are the final products, so it didn't really matter. But you are correct. We would have to add the H. If I just said stop at the enol, we would have both of those products. So for the alkyne reactions, most of them, with a couple of exceptions, are basically the same as what we did last semester, right? Which is either good or bad. You either remember it from last semester or you don't. So if you don't, you've got to go back through and remember those reactions. But we're only going to have truly Markovnikov addition if it's a terminal alkyne. If it's an internal alkyne, one of two things will happen. They'll either be asymmetric, in which you'll get two different products for any of the reactions, or they'll be symmetric, where it doesn't matter how you add because you get the same product either way. And I did release, after I did release some practice, ungraded practice problems in the folder from Wednesday. I think there may even be some from Monday as well about alkyne reactions. And when I give you a sheet of problems that we we'll work on in class if there's no other problems. Those would be good extra practice problems. So like the ones from Wednesday, I will go through and I will write sort of an answer key for those, and I will put that online either today or tomorrow or Sunday. I will put them on there when I get them done. So for the one for today, anything we don't do today, good practice problems, I will put that on there as well. And if there's something, the next period or on Piazza, hey, I don't get this, ask a question, and I will put it, and I will answer it. Because it doesn't do me any good to hand out problems and then there's no answers to them. Right, so this was hydration, which was different. The different reactions from last time from alkynes were when we talked about reductions on Wednesday. So H2 with palladium versus H2 with Lindlar versus sodium metal and liquid ammonia. Those gave you the possibilities of taking a triple bond all the way down to single, stopping at the double bond, but adding the 2 hydrogen cis or trans. That's new. This is new, that final step. So does that kind of make sense? Now, if we go back for the final hydration, let's go back to the terminal. We know how to do this reaction, Markovnikov addition. What about if I wanted to take and add the H and the OH anti-Markovnikov so that when this underwent the tautomerism, I wouldn't form a ketone, but instead I would form the aldehyde. What reagent would I use to do H and OH addition anti-Markovnikov? Go ahead. I didn't catch the last part. Yes. BH3H2O2, the hydroboration oxidation. So hydroboration oxidation with alkenes last semester, what did it do? It added H and OH. Anti-Markovnikov, what was the stereochemistry? 100% cis. Which is why this time I wrote the H and the OH cis. So you can take a terminal alkyne and you can add H and OH to it, Markovnikov to get the ketone or anti-Markovnikov to get the aldehyde. There is a problem. And I will accept BH3H2O2, but if we wanted to do this in the lab, we would not get 100% anti-Markovnikov addition. And in order to explain the reason why, we have to remember what happens with BH3 and then H2O2, which is perfectly fine. It's review. So how did that reaction occur last semester? Well, remember that the boron-hydrogen bond, the hydrogen is slightly negative and the boron slightly positive, because boron is one of those elements that's less electronegative than hydrogen. And so what we did was we added the B and the H at the same time to the double bond. Now I'm going to add it to the triple bond. So what's going to happen is my pair of electrons is going to move like this to form the CH bond, and then the triple bond is going to move out to form the bond to the carbon. And so I ended up going through what kind of transition state? I ended up going through a square transition state. And a square transition state means that the two groups are automatically going to add cis. Right? We had a square transition state when we added BH. We had a square transition state when we added the two hydrogens that were sitting on the surface of the metal. We had a 5-member transition state when we added the two OHs. 4 and 5-member transition states always cis. Triangle transition state means trans. And the boron added to the end carbon because of, why was the boron forced to add at the end? I thought I heard it. But you're a long ways away from me. And this room has an echo in it that's kind of driving me up the wall. Sterics. So in an alkene, we want the boron to add to the carbon that's least sterically hindered, which by definition is the carbon with the most hydrogens, therefore it's the anti-Markovnikov. The problem here is this. A triple bond is linear. On Wednesday we said, well, if you're going to use an alkynyl anion as a base, it's most likely going to act as a small base because it's linear and it's not sterically hindered. So in this case, our triple bond is not sterically hindered. And there's really not a whole lot of difference between those two carbons in the triple bond. So we go into our organic toolbox and we say, okay, if my reagent, or we could call it the organic tackle box if you'd like, we go in there and we say, okay, my reagent is not sterically hindered, so how do I accomplish my goal? I make the reagent sterically hindered so that I force the boron to add to the end. And so what we do then is one of the reagents we can use is what's called SiA2BH. And that is a boron with one hydrogen that has these two alkyl groups attached to it. The name is bad because the name is like even bad for common names where there are no rules. So SiA2 stands for secondary isoamyl, and that's what it is, secondary isoamyl. Amyl is a common name for pentyl. So oftentimes amyl is pentyl. So if you look at this, it's descriptive, it's wrong, it's a horrible name, but it describes what it is. It is a amyl group, a pentyl group, with an iso group where the boron is attached to a secondary carbon. Hence, secondary isoamyl. But it is a complete mess of a name. But that's what it's sometimes called. Sometimes people will take the boron. I probably should have looked up the exact reagent. But it looks something like this. We could take our bicyclic molecules from last semester and we have put a boron in the bicyclic ring with the H attached to it. So that would be another way to make a sterically hindered boron. One of the other reagents that's used is called 9BBN. I do not believe that's 9BBN, but it's the same general approach. So the idea here is if your reagent or if your reactant is not sterically hindered, you can accomplish the same goal by making the reagent sterically hindered. So if I make this boron then sterically hindered, it forces it to the end. And so I will get a much higher percentage of aldehyde than I will just using BH3. Will I accept BH3? Yes. But the reality is there are better reagents. And again, that fundamental concept of using steric hindrance to your advantage doesn't just mean the reactant is hindered. You can also make the reagent hindered. So that's how we would really do anti-Markovnikov addition of the H and the OH, and then it would turn into the aldehyde by tautomerization. So that's H-OH addition to alkynes, which are new. Everybody kind of with me? Any questions pop up? Still no questions? Then I will continue. The last thing that's new is cleavage. So we talked last semester about oxidative cleavage. What kinds of reagents did we use for oxidative cleavage? We used things like KMNO4 and acid. We used ozone with either H2O2 or R2S. Those were our examples of oxidative cleavage reagents. What did they do? They cleaved the double bond and turned each carbon into a carbonyl. Now, from last semester, if you cleave the double bond, you turn it into a carbonyl. The question was, what do you do with aldehydes? Do you oxidize them to carboxylic acids or do they stay? In these two, the aldehydes that were produced went up to carboxylic acids because those reagents, peroxide and KMNO4, oxidize aldehydes to carboxylic acids. Whereas in the case of the R2S, the aldehydes remain. So there was that. We had to know which reagent went with which transformation. Fortunately for triple bonds, we don't have to worry about that. And here's the logic behind that. The logic behind that is a carbon-carbon triple bond is far more stable than a double bond. So to cleave it, you're going to have to use a very potent oxidizer. Because if you use just some moderate reagent, it's not going to cleave the triple bond. It may do a good job for the double bond. It's not going to do it for the triple bond. So we got to use something that's very oxidative. So in the process of using a very potent oxidizer, I'm going to cleave the triple bond. I'm going to convert each carbon that was in the triple bond to a carbonyl. But because I have to use a strong oxidizer to cleave the triple bond, I have no choice but to convert those two carbons to carboxylic acids. So you only get carboxylic acids when you cleave the triple bond. So you don't have to remember any of those reagents. Oh, this one leaves an aldehyde. There are no aldehydes. If you're going to cleave a triple bond, you're going to leave nothing but carboxylic acids behind. So what reagents would do this? Definitely KMNO4 and acid, probably KMNO4 and acid, and some heat. If ozone's present, it's going to be ozone and peroxide, but ozone may not be enough to cleave the triple bond. So that's the only difference. That's the other reaction for a triple bond that is different than a double bond. You can definitely use this. You can definitely use KMNO4 acid. Although the book will probably say KMNO4 acid and some heat. It might even say boiling KMNO4. I guess I would accept ozone and H2O2, although I'm not quite sure if that will completely cleave the triple bond. The ozone and the R2S, no. Definitely, that's a no. That won't cleave it. There's probably some other super oxidizers out there. KMNO4 is probably the best. So that's what's different. So that's kind of cleans up the rest of the alkyne reactions. Everything else is like HBr. Okay, I'm going to add HBr, Markovnikov. One or two, okay, one or two. You add the first HBr, you make a double bond, you add the second HBr. You can add two equivalents. You can add two BRs or four BRs. One equivalent of BR2, two equivalents of BR2. So you have to remember from alkenes, what am I adding? How am I adding it? How am I adding it? What two groups am I adding? Markovnikov, anti-Markovnikov, cis, trans, 50-50. And I think I still have the chart that I think I had written out from last semester that I'll post in today's folder. Someone asked about a chart, a flow chart for determining meso and antimer's diastereomers. And I can't find that chart on my iPad. So I'm going to have to find it somewhere. I actually started drawing it out and then got distracted with other things. So I will put one of those together as well. Because all my flow charts are drawn out on my iPad. It's just I could probably create a ton of flow charts. I saw some really nice ones in Dr. Dowd's NMR things, which I just have as paragraphs. So I guess I'm going to have to up my flowchart game. But I will put the chart. If you don't remember or if you never had that chart, then you can go ahead and take a look at it for remembering those reagents, because we need to know them for now, for alkynes. Okay, so the problems that I gave you are for Chapter 14, which the first part of Chapter 14 is, it is not naming. The reason that naming is on those videos is because that's the Wade book. Wade broke out naming into each functional group. We talked about naming last semester all at once. So there is naming there, but the reason that I indexed the videos was so that you could immediately go to that section that is in the reading assignment. So if there's no naming in the reading assignment, you can skip over that and go directly to the topic at hand. So the first thing for any functional group is going to be structural, physical properties. There's probably some of that in terms of alcohols. I think in the video there's like alcohols, the hydrogen bond, yeah, great. Some you can drink, some you can't. Some will kill you, some will make you go blind. Others will probably make you do stupid things in excess. But you can deal with that on your own. The next step is, do we know how to make that functional group? So let's review. So do we know how to make alcohols? Yes. By what kinds of reactions? Let's review them. And so the reactions that I gave you on that sheet are all examples of things that we should know how to do. Now, I did not give you reagents to go ahead and mix and match, because you're not going to be able to match things on the exam. So ultimately, those reagents that you use have to be in here, because they're not going to be A, B, C, D. I may put the reagents on there if you want to, it's baby step. We need to be able to match them and then remember them. But how are you going to approach that? So for instance, if I said, what reagent or reagents can you use in this reaction, which is one of the ones on the back? A lot of the problems on the back are alkene reactions. So how do we add OHs to alkenes? Well, we'll have to get those reactions together. If you're making 3x5 cards or electronic 3x5 cards or whatever, or you're writing down the reactions, the advantage of cards is that I can take my stack of cards and I can say, okay, I need reagents to make alcohols from double bonds. There's 3. Which one would I use here? Hold on. So there are 3 reactions that we talked about to basically add H and OH to double bonds. But when I look at this molecule, okay, great. I need to add H and OH. How did I add the H and the OH? Markovnikov or anti-Markovnikov? Markovnikov, so that narrows down the list. So what reagent adds H and OH to a double bond Markovnikov? Tommy, you were all excited. H plus H2O. Right, so we'll circle back to where we started. Is there another set of reagents that will add H-OH Markovnikov? There is. It goes through. So mercury acetate, H2O, and then NaBH4. Mercuration, demercuration. We'll also add HOH Markovnikov. And in this case, since the product has, how many chiral centers does that product have? 0. It's got 0 chiral centers. Plus over here I've got 2 hydrogens. Did I add the H and the OH, cis or trans? Actually, I have no idea because there's 2 hydrogens. So doesn't matter. Doesn't matter whether I add 50-50 from H plus H2O or if I had 100% trans from the mercury. So I could use either one of those reagents to do that transformation. So the idea here is that these are review reactions from what we learned before on how to prepare alcohols. Then the next thing we do after we review is we learn new methods to prepare alcohols, which is going to be Wednesday's class on Grignards, Grignard reactions. So these are going to be new methods to make alcohols. And then once I learn all my methods to make that functional group, my final step is what can I do with alcohols? How can I transform those into other functional groups? Okay, so that's what those problems are there. I will post reagents, probably with a written explanation as to why I chose what I did. If you have any questions, though, put them up on Piazza, email me, come see me. But otherwise, for Wednesday, please look at the reading assignment from the book or the videos. On Grignards, we'll start with questions, and then I'll probably have a sheet of reactions as well that we can either work on, or I'm going to start cutting down on my lecture. I'm going to try and cut down on my lectures. That's why if you have questions, you got to ask, because I'd much rather do that and do some problems than. But if I just hand out problems and everybody looks, and then they start, looking through their notes, it's probably better I talk a little bit. But we hopefully will move to the point where we're doing more problems than me talking. Okay? All right, so we will not have an in-class quiz until Friday of next week, because Wednesday, with no Monday class, that's not appropriate time for our first inside quiz or our in-class quiz.